Vambora. Mais uma livezinha. Let's go. Voltamos, né? Tava bastante tempo sem live. E agora eu voltei. E, mano, vai ser todo dia. Novamente. Provavelmente quarta vai ter. Não vai ter como, mas o restante dos dias ali vai ser todo santo dia. Tá? Mas vambora. Hoje eu tô no Windows, então vocês podem imaginar que vai ser C, tá? Então segunda, quarta, sexta vai ser live de C. E o restante vai ser de Odin, então amanhã vai ser Odin Project. Quarta eu vou cortar o cabelo. Então. Quarta eu vou cortar o cabelo, então não vai dar, né? É, vamos lá. Agora a gente vai ver aqui. Então a ideia que eu quero seguir é a seguinte. Hoje a gente vê até uma parte. A gente vê esse vídeo aqui, como computadores funcionam. Tá, eu vi no coisa. Eu organizei aqui. Vou mostrar aqui pra vocês. Display Capture. Eu organizei aqui no Notion, tá? Eu vi num post do Reddit que a pessoa tava recomendando ali como que a gente estuda o C, né? Ele recomendou a gente ler Code, the Hidden Language of Computer Hardware and Software. Então, é código, a linguagem escondida de hardware de computador e software, né? Ah, então, tipo, esse livro, né? Seria um livro que parece interessante de ler. Então, tô pensando em ler em live aqui com vocês. Depois ele diz aqui, explorando como computadores funcionam, que é o vídeo que a gente vai ver. Depois ele diz aqui pra gente fazer um crash course, ah, que mostra ali como que faz tudo de computer science, basicamente. Depois fazer o CS50, que é interessante, eu quero fazer, tá? Quero fazer. Depois de terminar o Foundations ali, eu vou fazer, tá? E aí o foco vai ser totalmente, porque eu vou estar de férias da faculdade. Então o foco totalmente vai ser no coisa. E vou dar uma pausa, né? E depois a gente volta aqui pro Full Stack JavaScript, que a gente vai rever ali também. HTML, CSS e JavaScript e uh, Git, eu acho. Tá. Aqui eu utilizo aqui pra ver como é que a gente vê, mas eu acho que a gente vai ver tudo. A gente vai ver HTML, CSS, JavaScript, a gente vai ver algoritmos, memória, estrutura de dados, tudo e a gente vai ver C, tá? Então é interessante a gente fazer. Acho que vai ser legal. E eu pretendo fazer em live. Tá? Pretendo fazer nessas férias aí e aproveitar, né? Depois diz assim, pega uma cópia de C Programming Modern Approach. Eu já peguei, baixei. Mas eu não vou falar como que eu baixei, né? Mas eu baixei. E me parece um livro bacana que dá pra utilizar pra estudar. Depois aqui ele diz um tutorial de pointer. Ele diz aqui que esses quatro primeiros ah, são bastante interessantes. Eles assim, tu pode pegar dois, pode fazer os quatro, né? Os quatro. Tu pode pegar um ou dois e mergulhar fundo. Eles que o quinto é uma boa introdução para a ciência da computação, com uma quantidade decente de programação em C, né? E o sexto é o melhor tutorial de C, ele falou, por muito. E o sétimo é o mergulho. É o mergulho fundo, né? É em ponteiros e um dos melhores tutoriais em ponteiros e arrays. Aí, pela internet. Depois ele dá ali links de practical tutorials, que project based learning, que é o que eu quero fazer. Play the long game when learning to code. You can also check out Teach Yourself Computer Science. Parece ser interessante também. Tenho aqui dá vários livros aqui para ler. E eu pretendo ler bastante livros aqui ao vivo com vocês, né? E estudando. Então acho que é interessante a gente fazer isso futuramente, depois do Foundations. Eu vou fazer o CS50 e depois eu vou voltar pro Foundations. Então, o foco dessas férias vai ser o CS50, né? Então, o Foundations a gente falta quase nada. Tá? Falta fazer um project ali rapidinho. Tá? Não era pra demorar tanto, tá? Mas eu tô enrolando, então. Mas assim, esse projeto a gente vai terminar essa semana, tá? E aí semana que vem vai ser Object Basics e depois o último projeto, que aí a gente vai se aprofundar, então vai demorar um pouquinho. E aí, eu acho que vai ser interessante, tá? Tô pensando em ler livros e colocar no meu Kindle. Então é isso, eu fiz esse planejamento. Então a ideia seria ler isso aqui. Eu acho que eu vou botar no Kindle pra ler. Então, falar a real mesmo. Eu vou botar no Kindle pra ler. A ideia seria, primeiro, tá? Eu ia seguir isso aqui, eu ia ler isso aqui, é um livro, né, também. Então eu ia ler, basicamente, um livro em HTML. Então eu iria ler isso aqui, ver, usar o livro como base, e ver o vídeo do Akita, fazer parte de Base Learning, segunda, quarta e sexta. Tá? E futuramente fazer o CS50. E aí, nos outros dias seriam ahn, apenas The Gym Project. E eu vou ver de ler esse livro aqui, tá? Vou ver de estudar, fazer o Kindle, velho. Vou ver isso. Acho que é interessante. Vamos lá. Agora a gente vai ver esse vídeo aqui. Vamos ver se esse vídeo é bacana. Ahn, Isso aqui não me parece inglês.
One, I spend a lot of time mashing away at a keyboard trying to tell the computer what I'd like it to do. Even my
Ahn, E aí depois a gente ia ver esse vídeo aqui, tá? A gente vai começar a ver esse aqui.
Remember that when he says relative.
Hey guys.
Então, rapaziada, a live de hoje vai ser bem curta. A gente vai ver esse vídeo aqui, explorando como os computadores funcionam. E aí
Remember that when he
eu vou encerrar, tá? Pra ir quarta, talvez não vai ter live. Provavelmente eu vou cortar o cabelo. É. Daí, quinta e sexta a gente focaria nisso aqui. Eu queria ver esse vídeo, então eu queria ver totalmente esse vídeo. Dá pra eu pelo menos ler. Acho que eu vou ver esse aqui e pelo menos ler esse Far Wars aqui, tá? Eu vou ler tudo isso aqui. Tá, então a gente vai ler isso aqui tudo. Será que dá? Tá, acho que dá.
Pensa no mundo comercial. E claro, na computação científica. Olá,
Hi everyone. I spend a lot of time mashing
For the past 2 years, I've been using the C programming language for almost all of my projects. This video is about my journey through being completely clueless to relatively okay at the language.
I like the honesty.
away at a keyboard. Trying to tell the computer what I'd like it to do. Even my oddly shaped computer that constantly gets teased for looking like a trash can is unbelievably good at following instructions. Unfortunately, I'm not so good at giving them, so the results are inevitably a little wonky. But nevertheless, it's always been such a mysterious thing to me that this inanimate lump of metal and sand and whatever else, arranged in some extremely clever way, is able to do maths and logic and remember things, and ultimately allows us to create pretty much anything we set our minds to. It's kinda bizarre, and I'd really like to understand better how it works. So here's a little circuit with a light and two switches, A and B, and clearly the light can only go on if I close both of these switches. Already this is a kind of simple logic. We're testing if two conditions are true, switch A is closed and switch B is closed. If we represent an open switch with a 0 and a closed switch with a 1, these are the different configurations we could have. And here's the output, 0 meaning the light would be off, and 1 meaning it'd be on. Since that's only the case when A and B are 1, this is known as the logical AND operation. And this kind of table, by the way, is called a truth table. Here's a bit of a different circuit. This time we only have one switch, and even though it's open, the light is currently on. If I close the switch, now the light will go off, because we've created an easier path for the current to travel. So we're essentially inverting the input. If the state of the switch is 0, the output is 1, and vice versa, and this is known as the logical NOT operation. Now, I've been controlling these switches with my fingers, which computers sadly lack. So in the very early days, electromagnets were used to open and close the switches, but this was kind of clunky and slow, so then came fancier technologies like vacuum tubes, and finally transistors. As a tiny example of what transistors do, this is essentially that same NOT thing from before, just set up on a breadboard and with a transistor in the place of the paperclip switch. If we think of the current flowing in this circuit, it would look something like this. It can't flow through the transistor at the moment because right now it's acting as an open switch. But if we send power to the middle pin of the transistor, establishing a small flow of current like this, the fancy physics of the transistor will make it act like a closed switch instead, allowing the main current to flow through it like so. Just like before, the light is turned off because we've created a much easier path for the current to take. So essentially the transistor is a switch which we can open and close with electricity instead of our fingers. I'd love to one day try and build a simple computer out of components like this, which is what Ben Eater has done in his very cool 8-bit breadboard computer series, but that's a little intimidating for me at the moment, so instead I've made a simplified and abstracted little simulation where we have our two logical building blocks and not, and we can play around and try figure some stuff out. So on the left here are some inputs which can be turned on and off, or we can also think of it as true and false or 1 and 0, it doesn't really matter. But I'll wire these up to the inputs of the AND gate, and if you recall my sophisticated circuitry from earlier, the two inputs simply control whether these switches are open or closed, which should be achieved using transistors, not paperclips of course. Now I'll connect the result of this AND gate up to my output node over here, and so this will only light up if both inputs are on. Let's get the NOT gate participating as well, so I'll connect it up over here and wire the result of that to the output instead. So the output is now inverted, it's off when both inputs are on, but in all other cases it's on. Here's a truth table for this thing we've just built, and it actually has a name. This is the NOT AND, or rather NAND gate. If I click on the Create button down here, it'll package that up into its own little chip, and we now have a NAND gate to mess about with. I guess this is a good moment to mention NAND to Tetris, which along with Ben's videos is a fantastic free resource I've been using to learn more about this stuff, so I recommend checking that out if you're interested. Anyway, to take this a little further, we could maybe try inverting both of the inputs before feeding them into the NAND gate, and let's see what that does. So with both inputs off, the output is off. If I turn either of them on, the output goes on, and if both are on, the output is still on. So we've created what's called an OR gate, and I'll turn that into its own little chip as well, because it seems pretty useful. And here's the truth table for that. Alright, let's take a moment to think about something that's pretty important to computers: numbers. In the decimal system that we know and love, there are 10 digits, 0 through 9, and if we want to go higher than that, we need to add another place to the left, where each digit actually represents 10 times as much as those in the previous spot. And we can have as many places as we need, so here would be hundreds, then thousands, and so on. In the realm of electronics, though, it's easier to work with just 2 digits, because they can be naturally represented with a low voltage or a high voltage. So this binary system works in the exact same way as the decimal system, it's just that once we reach 1, we've already run out of digits, and so we increment the place to the left. Because there are only 2 digits in binary, each place is worth 2 times more than the last. So if the first place is worth 1, then this place is worth 2, then 4, then 8, and so on. So let's say we want to figure out what this sequence, 1101, would be in decimal. Well, we can write it out as 8 times 1, plus 4 times 1, plus 2 times 0, plus 1 times 1, and that comes out to 13. Alright, now what I'd like to do is design something that's able to add two binary numbers together. So let's work through a quick example by hand. Say we want to add these two together. Starting on the right here, 1 plus 1 is 2, which in binary is 1, 0. So I'll write the 0 down here, and then carry the 1 over up here, because we'll need to add it together with these other two in order to figure out what goes in this spot. By the way, this part that we wrote down here straight away I'll refer to as the sum bit, and this one up here is the carry bit. Okay, let's continue. 1 plus 1 is 2, plus the carry gives us 3 in decimal, or 1, 1 in binary. So I'll write 1 over here, that's the sum bit, and carry the other one over to the left. Now we have 0 plus 1, plus the carry bit is 2 again, so I'll put 0 down here and 1 up here. This will just give us 1, so I'll write that down here. Then 0 plus 0 is 0, and finally 1 plus 0 is 1. In case you care to know, what we've just calculated here is 35 plus 7. It's a little daunting to try start thinking about how we can wire our logic gates together to do all of this, so let's start small with adding together just two single bits. For example, if we're adding a 0 and a 0 together, then naturally both the carry bit and the sum bit will be 0. But if the first bit is a 0 and the second is 1, or the other way around, then the carry bit will be 0 and the sum bit will be 1. Finally, if both bits are 1, then the carry will be 1 and the sum bit will be 0. So if we look at the carry column here, it might look familiar because it's actually an exact match with the AND operation. The sum column, on the other hand, doesn't match exactly with anything we've already seen, but it's quite close to the OR gate we created earlier. It just has a 0 in this last spot instead of a 1. So let's take that OR gate as a starting point, and we just need to turn the output to a 0 when both inputs are 1. So I'm going to take a NAND gate and connect it up here, and this will check if both inputs are 1, and then invert the result, so that it's outputting 0 in that case. We can then use an AND gate to check if either of the inputs is 1, but not both of them. Let's test this quickly. With both inputs off, or 0, the output is 0. With just a single input set to 1, the output is 1, but crucially, when both inputs are 1, the output will be 0 again. This operation has a special name as well. It's called an exclusive OR, XOR for short. Okay, so I now have an empty chip with two inputs which we want to add together, and two outputs, the sum bit and the carry bit. So we can use our new XOR gate to calculate the sum bit of the two inputs, and then remember that only if both inputs are 1 should the carry bit be 1, and so we can simply use an AND gate to test for that. So that's everything we need to add two bits together, but of course in some of the steps we actually had 3 bits we needed to add together because there was a carry bit from the previous step to deal with. And in fact we could think of these other places as having 0 in the carry spot, so in a way we're always adding 3 bits together. So I'll introduce a third input to the chip over here for the carry input, and we need to add this to the sum of the first 2 bits which we calculated up here. To do that, we can simply
Não, já me perdi, mas eu tô entendendo, Tipo, eu me perdi, mas eu tô entendendo. Maluco. Mano, é foda. É foda. Maluco. Mano, é foda. É foda. Maluco.
Simply use another XOR gate wired up to that carry input and to the sum of the first two inputs. We'll then need a second AND gate as well, because if the sum of the first two bits is 1 and the carry input is 1, then we'll need to carry 1 to the next step. So if either of our two AND gates detect that we should be carrying 1, then we'll of course want to output 1 to the carry output, which we can do using an OR gate. Let's check if this is working properly. So with all of the inputs off, or 0, both the sum and the carry output bits should be 0. Then if any single input is 1, the sum should be 1 and the carry should be 0. So far so good. Next, if any two inputs are 1, then the sum bit should be 0 and the carry should be 1. And finally, if all three inputs are 1, then the sum should be 1 and the carry should be 1. And it looks like it's all working, so I'll give it a name, and then what I'd like to do is take this adder we've made and use it to construct a 4-bit adder capable of taking these two 4-bit numbers that we have as our inputs and calculating the 4-bit sum as the output. I've added these little displays, by the way, to tell us what all these values are in decimal, just so it's a bit easier to tell if this thing is working. So we'll need 4 adders to construct this, and I'll wire each one up to the outputs. Then there's a carry input here, just in case we want to string two 4-bit adders together to make an 8-bit adder, for example. So that can go into the carry input of the first adder, and then its carry output goes into the carry input of the next one, and so on down the chain. Finally, I'll need to connect up the two 4-bit inputs. Let's test this out. So right now we have 0 plus 0 equals 0, which is a good sign. Let me try 1 plus 1, 2 is correct, 5 plus 1 is 6, and 7 plus 1 is 8. So it looks like we can add numbers together, which is pretty cool. Of course, with just 4 bits, if we try to do 15 plus 1, for example, it will overflow to 0, because we don't have enough bits to store 16, and the carry bit will light up over here, telling us the result was too big for 4 bits. If we want to extend this to handle subtraction, we'll need a way to represent negative numbers in binary. I always assumed that this last spot was used to indicate the sign of the number, so what we have here would be positive 7, and this would be negative 7. But of course, you'd expect that if we added 7 to negative 7, we'd end up with 0, but that's clearly not the case here. So one way we could try thinking about this is what would we have to add to 7 in order to get 0 as the result? Well, in order to get a 0 in the first spot, this would need to be a 1, because remember 1 plus 1 gives us a sum bit of 0. Of course, we also now have to carry 1 to the next spot. So now we know that there should be a 0 here, so that we'll again have 1 plus 1 giving us a 0 for our sum bit, and a carry of 1.
0.
We can then deduce that there should be a 0 here as well, and we can continue like
1.
this to end up with all zeros for our 4 bits. There is a 1 that ends up over here, but since we're working with just 4 bits, that can be discarded. So we figured out that -7 must be 1001.
Que é 81? 9?
That might seem a bit weird, but it actually makes some sense if we think of this last spot as the -8 place, because then we could write this out as -8 times 1, plus 4 times 0, plus 2 times 0, plus 1 times 1, which gives us -7. Let's start at 0 and see what it looks like now if we count up. So 7 is now the largest number we can have with 4 bits, and it then flips over to the smallest number, -8. And from there we have -7, -6, -5, -4, -3, -2, and finally all ones would be -1. So it's a bit of a funky system, but it allows us to add negative and positive numbers together without any fuss, so it's totally worth the weirdness. Now, there's actually a simple two-step procedure for making any positive number negative. Take the number +6, for example, 0110 in binary. The first step is to invert all the bits. So where there's a 0, we write a 1, and vice versa, giving us 1001. At this point, if we were to add these two together, we'd obviously get all 1s. We want it to be all 0s though, and we saw a few minutes ago that if we take this and just add 1 to it, we'll end up with 0 for the 4 bits we're interested in. This tells us that clearly our inverted number is just 1 too little to give us all 0s. So the second step, as you might predict, is to take the inverted number and just add 1 to it. So in this case, we'd take 1001 and add 1, and that would give us 1010. And if we look back at the number wheel, that is indeed -6. So, using that 4-bit adder we built, we can of course add these two 4-bit numbers together, but if the subtract signal over here is on, then I want to subtract the second number from the first, which we can do by making the second number negative, and remember we do that by inverting the bits and then adding 1. So, to invert the bits, we need something that looks at the subtract signal, and if that's off, the input bits should be unchanged, but if the subtract signal is on, then the bit should be inverted. Conveniently, this table actually matches the exclusive OR we made earlier, so we can just use 4 of those to invert these bits only if the subtract signal is on.
É, eu teria que ter lido esse livro, eu acho, mano. Porque eu não entendi nada.
The last step of negating a number was to add 1, so we can just feed the subtract signal into the carry input of the adder, and that'll do that for us. Alright, I'll quickly go ahead and wire up the rest of the inputs, and then output the result. I also have these 3 extra outputs, and these are just for flagging some stuff about the result. This one over here, for example, tells us if the result was 0, and we can test for that, like so. This other output tells us if the result was negative, which is true if our -8-bit is set to 1. And finally, there's the carry, which I can just take from here. and this is just information that'll be useful to us later on. Let's now test if this is actually doing what we want, so I'll try 3 plus 4, and that's 7, so it looks like we haven't broken addition at least. Now I'll try turning on the subtract signal, so we're doing 3 plus -4, which of course is the same as saying 3 minus 4, and the result is indeed -1, so that's good. Let me try -2 minus 4, and that gives us -6. Then let's see if it can handle subtracting a negative number, so I'll try -2 minus -4. Even that seems to work, we get +2. I want to test one last thing, which is adding 2 negative numbers together, and once again the math seems to check out. So this is going to be our arithmetic and logic unit, although to be honest it doesn't actually do any logic. There would just be things like doing the AND operation on the inputs and outputting that, for example. But we can expand this later if necessary. For now, I'll call it ALU for short, and package it up into a tiny little chip. So that's going to be all for this first episode. I hope you found it interesting, and in the next one I want to look at how memory works, because I'm very curious to learn more about that. Until then, cheers!
Caralho, que loucura, mano. Muita coisa pra aprender.
I get asked all the time in stream channel if C is the appropriate language for the future when it comes to systems programming. I think that Rust eventually will take over for C. We're not talking about that today. One, this is not sponsored. This is not an into the holy war of whether or not C is a high or low level language. For the purposes of this video, C is a low level language. Discuss in the comments. Learning to code effectively in C forces you to learn effective memory management. It forces you to learn how to write code that is bulletproof, because if you don't, the code will just inherently be unsafe. There are lots of things you have to do in C to not leak memory, to not give your code access to hackers, and to not have the code just crash whenever it runs. The number one project I tell people to write when they're trying to learn to code, maybe they know the language but don't have a project to go after, is to write an HTTP server. And I know that sounds fairly advanced for somebody maybe new to a language, but it will teach you not only the ins and outs of the HTTP RFC, but a lot of really important things about programming. For example, when you're writing the HTTP parser, you have to not only write the code that adheres to the RFC, but then you also have to think of your code defensively. You're going to be in processing and reading code from literally anybody on the internet. You have to treat your code as if it's being attacked. You have to code defensively. Writing an HTTP server will allow you to get really familiar with how to read the documentation of a language. You're not just going to know the networking stack off the top of your head. You have to learn how to read man pages, read documentation, and read how return values work in the language of your choosing. I think learning C teaches you how computers work at a fairly
É isso, rapaziada. Vejo vocês amanhã. Amanhã vai ser Origin Project. Quarta, provavelmente eu não sei se vai ter live. Mas aí, quinta e sexta, a gente vai focar em C. E é isso, rapaziada. A gente vai focar em C. Eu vou querer... hoje a gente viu esse vídeo, mas eu não entendi nada. Então, semana que vem o foco vai ser em C. Então, o foco vai ser... Eu vou querer ver esse vídeo. A semana que vem, quinta. Quero ver esse vídeo. E eu quero... começar a ler esse livro aqui. Então a gente vai estar lendo e pá. E é isso.